We have learned many things so far, and if I can review it for us, in chapter 1.1 we learned about the functions, and we continue with the transformations on 1.2 that talks about the translations, dilation, and then reflections. In 1.3 we learn about linear and quadratic functions and how it can be useful in our real world problems, such as how to get the maximum profit using the quadratic functions, or how to get the break-even point using two linear functions. In 1.4 we learn about the polynomial and rational functions, and last lesson 1.5 we learn about the compound interest and compound continuous interest using the Euler number, and that is using the exponential functions. So what is the logarithmic functions? From what we have learned in 11th grade, if you don't remember, I'll remind you again. Logarithmic function is the inverse function of an exponential function. I know there are many functions over there. So what is the inverse of a function? That's the thing that we need to understand first. I'll put it this way. If we have an input, let's say x, and then this input is having a process of f of x, and then it gives us the output, which is a f of x. I know this f of x and this f of x has a same symbol, but it has a different meaning. The x over here is the input, and then the f of x over on the last one will be the output, and then in the middle is what we call as the process or the functions of it. Let's say I want to have, instead of x as the input, I want to have a f of x as the input. So I reverse the process. It will be, the arrow will switch into the opposite directions, and then I will need another functions, okay, that can produce the x as the output. Now that functions in the middle will be f inverse of x. So this is the inverse of a function. Inverse of a function is the reverse process of the function. I'll give you an example. Let's say we know the relations between the Fahrenheit and the Celsius. Fahrenheit, by the way, is a temperature, if you don't know. Okay, Fahrenheit is expressed as 9/5 Celsius plus with 32. So let's say if we have the Celsius is equal to 0, then what is the F? If Celsius equal with 10 or Celsius equal with 20, then what is the Fahrenheit? This has a meaning if C equal with 0, so we put it into the equations, then 9/5 times with 0 plus with 32 will get F equal with 32. If the Celsius is 10, then we'll have 9/5 times with 10, which is 18 plus with 32 will get F equal with 50. And then if the C is equal with 20, we'll get the F is equal to 68. Okay, now what if I have another problem? I'll put it this way. If I have F equal with 41, or if I have F equal with 50, or F equal with 59, what is C? Some of you will say, mister, it's quite easy. We'll just put the 41 value into here, and then we'll subtract 32, and then divide by 9/5. Yes, we can do that, or we can create a new formula. Okay, a formula in a new form. So we'll have C equal with F minus 32 times with 5/9. If you wonder how we get to this, it's actually by having subtract 32 on both sides on the first equation, and then we'll get f equal with 9 over 5c, and then this is f minus 32, and then times it with 5 over 9, 5 over 9. So we'll have this one. So I can say that the Celsius, the first equation, okay, has the inverse functions, which is c equal with f minus 32 times with 5 over 9. So basically, the inverse function is swap or interchange the x and the y, the input and the output, x and y also. So if I have a y equal with 2 to the power of x, I can also put it as a x equal with log to the base 2 of x. Now notice that y equal with 2 to the power of x is the exponential function. So the inverse of it, I'm sorry, this one is wrong. It's supposed to be, it's supposed to be y. Okay, so this is the logarithmic function. Let's see what the graphic look like. So I put it over here. The red dashed line is the exponential functions, and if I reflect it to y equal with x, this is what I'm going to have, the blue line, okay, the blue curve I mean. And if I switch the a constant by sliding from 2 and I decrease it, this is what's going to happen. It intersect at 2 points over there because that's the reflection. And what happens if I lower the numbers below from 0 to 1? Okay, so I have 0.754. You see that it decreased exponentially for the red dashed line, and it is the reflections is the logarithmic form, which is the blue line. Okay, so if it is like that, then we can put it in the definitions of one-to-one functions. If we always, when we want to inverse a functions, we always draw y equal with x because that's the reflections line. And let's say if I have it like this, okay, then the reflections will be something like this. This is y equal with log to the base a of x, and then the other one will be y equal with a to the power of x. I know this is same y, same terminology. I shouldn't use that, but you can change it with g of x, f of x, and h of x. Okay. About the one-to-one functions, a function f is said to be one-to-one if each range value corresponds to exactly one domain value, or we say that one-to-one function is invertible functions. It means that it can be inverse, okay, invertible function. Now let's try to understand this more. One-to-one function, a function f is said to be one-to-one if each range, so I can change that, if one, let's say 1y correspond to exactly one domain value, okay, which is the 1x. Now in the functions definition, we have one x, okay, one independent variable correspond to one dependent variable, which is 1x has only one y. If you have one-to-one functions, then since this is a function, it has this understanding, 1x has one y, and it also gives us another definitions that one y has only one x. So by saying that, we can simplify that 1x has one y and one y has also one x. That is one-to-one functions. Exponential function, logarithmic function is one-to-one functions, and it's also the invertible functions. But is there any functions that not invertible? Yes, there is. Things like the quadratic functions. Yeah, the quadratic functions, you can have like 1x equal with 1y, 1x equal with correspond to 1y, but when you put it to the reflections, okay, you will have that it is this, it will be something like this, that 1x has more than 1y. Yeah. Okay, let's continue to the next. This is by the definitions, so I read it again for you. The logarithmic functions, the inverse of an exponential function is the logarithmic functions, like what we have discussed. You have the logarithmic form y equal to log to the base b of x, and it's equivalent to x equal with b to the power of y. This also present the graphic that we discussed before, so I'll be quite brief on this one. But you have to be able to switch the logarithmic form into the exponential form and the exponential form to the logarithmic form. So perhaps you have learned a to the power of b equal with c. This is the exponential, and then we can switch it as a b equal with log to the base a of c. So if you're given let's say square root of 7 to the power of x plus 3 equal with 9. How to get the x? So if you understand the logarithmic form, then you can just switch it to x plus 3 equal with log to the base square root of 7 of 9, and then use your calculator to find this value and then subtract with 3 in the end. What if you have let's say log to the base x plus 4 of 3 equal with 2? Then what you need to do is to change it into the exponent form. So it will be x plus 4 square equal with 3, and then from here you use the you have a square of it and then subtract with 3, and then you'll get the quadratic formula to find it. So remember, a logarithm is an exponent. Many times I also find that you have a difficulty to pronounce this one. This is the log to the base b of x. Yeah, this is how we pronounce it. And then the domain and the range. This one I'll leave for you to read it by yourself. It's on your textbook. Everything that I say is on your textbook. Okay. If we understand this, then it will be easy for us to understand the properties of logarithmic functions. Now, if you have like number 1, log to the base b of 1 equal with 0, this has a meaning. If you change it to the exponential form, this is like b to the power of 0, that's equal to 1. Number 2, that is b to the power of 1 equal with b. Number 3 is a b to the power of x equal with b to the power of x. And then number 4 is to change the exponential function, okay, since it's an exponential function, into the logarithmic function. So you'll have log to the base b of x equal with b to the power of x. I'm sorry, it's get wrong. It's supposed to be log to the base b of x. So notice that you have b log to the base b of x. This part, okay, is getting to here. Okay, consider that this is the a. Yeah, then this will be a equal with something, and then you'll get log to the base b of x. Number 5 to 8, this using a derivations which you have learned in 10th grade. So I will not review about this one because it will take too long. Okay, keep in mind, if you have log to the base b m times with n, that is log to the base b of m added with log to the base b of m, and so on with this. Yeah, make sure that you understand so we can do this kind of problems. So let's try to do it some numbers. Number 1 until 12 is actually having a process of changing the exponential to logarithmic or logarithmic to exponential. Like number 1 to 6, you are asked to change it to the exponential form from the logarithmic form. If I do number 2, then I will have 2 to the power of 5 equal with 32. Yeah, number 4, then it will be e to the power of 0 equal with 1. So number 6, that will be 9 to the power of 3 over 2 equal with 27. This is a good practice. If you're not familiar by changing the exponential to logarithmic or logarithmic to exponential, I suggest that you do all these numbers instead only the odd numbers. Yeah. So number 8, it asks you to change it to the logarithmic form from the exponential. So number 8 will be 2 equal with log to the base 6 of 36. Number 10, it will be 2 over 3 equal with log to the base 27 of 9. Number 12 will be x equal with log to the base b of m. There's not much that I can say about this unless you do the practice by yourself. Yeah. Okay, let's move to the next one. Evaluate the expressions without using the calculator. So number 13 to 34 is not using calculator. So what you need to do is to understand the properties of the logarithmic functions like this. Okay, so we'll be able to do it. Okay, like number 14, we can have log to the base 10 of 10 to the power of 5. So we know that the answer will be 5. Number 20, when you have ln, okay, it means that you have log to the base e of e to the power of negative 5. This is same by saying negative 5 as the answer. So keep in mind, if you have e to the power of negative 5, this is also same by saying 1 over e to the power of 5. Yeah. This is to do the hint for number 19. And number 22, write in the term simpler forms. So you'll have, I don't know, I think this is already simple, but maybe he wanted to be like this: log to the base b of f added with log to the base b of g. Okay, this is not in simple forms, by the way. And number 24, that will be 15 log to the base b of w. Yeah. Number 26, it's quite interesting to have this. You can also put it as this: log to the base 5 of p over log to the base 5 of r. Or you can have also ln p over ln r. Or you can put any number as the base over here. So this, if it put it on the simpler words, it will be log to the base r of p. Yeah. And let's have number 34. 34, you have log to the base 25 of x equal with half. So what we need to do without using calculator is to change it to the exponential form. So in this case, it will be 25 to the power of half equal with x. So we'll get x equal with 5. Yeah, x equal with 5. That's quite simple. Okay, and yeah, the other one, I'll leave that to you. Let's have the next. So number 39 up until 52. Is this the last one? Let me check. Apparently it's not. We have one more page. Okay, so number 46. I'll do number 46. So log to the base b of x equal with 3 log to the base b of 2, and so on. Okay, so since we have the same thing over here, we can just write it as, we can write it like this: log to the base b of 2 to the power of 3, and then log to the base b of 25 to the power of half minus log to the base b of 20. And if we use the properties of logarithm, we can have, if you have the additions, it will be a multiplications over here if the base is same, and if you have subtractions, it will be divided by this one 20 over here. So you try to find what's the number of this, and you will be able to find the x. Yeah. Same thing with number 50, but number 50 you might want to change 1 into log to the base of 10. Yeah. Number 51, it says graph problems 51 and 52 by converting to exponential form first. So you'll have that if you convert it to the exponential form, it will be 2 to the power of y equal with x minus 2, or we can put it as a 2 to the power of y added with 2 equal with x. Yeah. So this is the inverse of it, or you can say interchange the x and y, so you'll have a better shape, 2 to the power of x plus with 2. It means that it has a translation shift up 2 units. Next, this one is quite easy because we are allowed to use calculator. But even you are allowed to use calculator, I hope that you know how to use your calculator. So you just put it, this one, number 58 to 60. Yeah. Of course, when you want to find log of x, what is the x? So you need to change it to the exponential form. This will be log to the base 10 of x. Even it didn't put 10 over here. This is a common logarithm. Yeah, so it didn't put 10. And log to the base 10 of x equal with negative 1.1577. So x equal with 10 to the power of negative 1.1577. Yeah, your calculator will have these functions, which is x to the power of y. Okay, try to find it on your calculator, or y to the power of x. I'm sorry, y to the power of x. Okay, and then the rest like this. Yeah, it will be quite easy. The thing is that you must be able to change between the exponential to logarithmic and logarithmic to exponential. Yeah, so like this, you'll have 4t 4t equal with log to the base 1.02 of 2. After that, t equal with